Hi all! So this is my surprise for you all. This video is about tips and tricks for chemistry SK015 chapter 7 Ionic Equilibria. Of course, don't forget, have you subscribed Tiger and Cat channel by Chemical? If you haven't, please view, share, like, comment and subscribe. Thank you. This video will divide to 5 parts. First part is about acid and base. Second part, calculation of pH and pOH. Third is salt. Fourth is buffer solution. And the last part is about solubility equilibria. Part 1, acid and base definition. First of all, you must know the definition of Arrhenius acid and base, Bronsted-Lowry acid and base, and Lewis acid, Lewis base. So, as I said before, the most common one is Bronsted-Lowry. When an equation is given, right, you must write an equation. Then, if you blur, not sure, confused, right, you always stick to Bronsted-Lowry as acid or base definition. If given is an acid, right, you must remember acid always donate a proton. And then base can accept a proton. Okay, if you stick to this Bronsted-Lowry acid definition, it won't be a problem for you to write a correct equation. Okay, and another tips for you all, if Ka is given, meaning that one is started from acid, Kb started from base. Next is about conjugate acid and conjugate base. Actually, conjugate acid and conjugate base is referred to the Bronsted-Lowry acid and base. So for example, conjugate acid. Conjugate acid is a species formed when a Bronsted-Lowry base, okay, look at here, this is the base. So if according Bronsted-Lowry base, it will accept a proton. After it accepts a proton, it becomes HCN. So this is the conjugate acid. So meaning that at the reactant side is a base, then product will become the conjugate acid. Same for here, for the conjugate base is formed from the acid, Bronsted-Lowry acid. Bronsted-Lowry acid donate proton. One is donate proton, it becomes NH3. So this is conjugate base. When the question asks about conjugate acid, conjugate base, always is referred to the product. Be careful. So next is about strong acid, strong base versus weak acid, weak base. So you have to always remember the keywords for strong acid or strong base is 100% ionized, dissociate completely, high concentration, and with one-way arrow. If for the weak acid or weak base, partially dissociate, partially ionized, low concentration, and with the reversible arrow. Okay, so there are a few examples for the strong acid, weak acid, strong base, weak base. Don't forget, if Ka or Kb value is given, meaning that the reaction is the reaction for weak acid and weak base. So it is using the reversible equation. And then if the question asks about the Ka expression or when you need to calculate something, you must write the Ka or Kb expression. The concept still the same, product over reactant. Ignore solid and liquid. Okay, you must have a concept about stronger acid, higher concentration of H3O+, larger Ka value and lower pKa value. Ka and pKa is inversely proportional. Smaller Ka value means lower percentage of acid dissociated, weaker acid. And same for the Kb, stronger Kb, higher concentration of hydroxide, larger Kb value, lower pKb value. So this is the example from tutorial question 11. So based on here, Kb is given, meaning that here refer for the weak base. So the question request to arrange the compound in order of increasing strength of base, meaning that when Kb increase, okay, this is the if Kb increase, meaning that stronger base. So over here, ammonia is the stronger, but order of increasing, meaning that the last one is ammonia. Okay, for part B, give the structure of conjugate acid. Okay, this is base. According to Bronsted-Lowry base, it will accept proton, meaning that all of here will accept a proton. Okay. We must have a concept. When this one is the strongest base, automatically it will become the weakest conjugate acid. So when it becomes the conjugate acid, it is the weakest acid if compared to the others compound. Okay, let's check the answer. Yes, this is the strongest base. Okay, increasing strength of base. The way to answer the sequence of an question, you must show the smaller or larger. In this case, increasing. So increasing strength of base. Okay, you see here. Just now, as I mentioned, strongest base, right? It will become the weakest acid. So this is increasing strength of acid. All of here is as a base. When it becomes the acid, it will accept a proton. That's why NH3 positive, NH3OH positive, N2H5 positive, NH4 positive. Clear? Part 2, pH and pOH calculation. These are the few formula that involved in the calculation of pH and pOH. So you should know Kw actually is 1.0 times 10 to the power of negative 14 is a constant. Is concentration of acid times the concentration of base. pOH plus pOH equal to 14. The P is referred to negative log. The calculation will be divided to 3 parts. So this is the first part for the strong acid or strong base. Strong acid, strong base dissociate completely. Normally we straight away using the concept pH equal to negative log concentration H plus, or pH equal to 14 minus pOH. Okay. So case 1, strong acid. So based on the equation 1 mole, 1 mole, 1 mole, we can straight away take the concentration of the acid is equal to the concentration of H plus. So pH equal to negative log, concentration H plus equal to negative log 0.1 molar equal to 1. Okay, same for case 2, strong base. So if strong base, we are referred to pOH. If you want to find the pH for a base, we need to apply pH equal to 14 minus pOH. So this is the answer. Okay, case 3, be careful. This case is involve 2 mole of hydroxide. So given the concentration of 0.1 molar of calcium hydroxide, so what is the pH in this case? Okay, again, base, we need to deal with pOH. So over here, 1 mole of calcium hydroxide gives 2 mole of hydroxide. So the concentration of hydroxide is equal to 0.2. So pH equal to negative log concentration hydroxide equal to negative log 0.2 equal to 0.699. And then if the question asks about pH, 14 minus pOH. So this is the answer for pH of 0.1 molar of calcium hydroxide. Okay. Second part is the calculation pH and pOH involve weak acid or weak base. How do you know the question is involve weak acid or weak base? Sometimes based on the question, it will mention is weak acid. If didn't mention weak acid or weak base, you can refer the Ka or Kb value. When the Ka or Kb value is given, meaning that that question is related with the weak acid and weak base. So if weak acid, weak base, the step of calculation pH and pOH not straightforward. You have to write an equation, form the ice table. Always remember the equation must be reversible equation. Don't forget about the phase of each of the ion. And then start from initial concentration, change of concentration, and the concentration at equilibrium. Next, write the Ka or Kb expression. If the Ka or Kb is equal or smaller than 10 to the power of negative 5, you have to assume, you have to make the assumption. If larger than 10 to the power of negative 5, you just do it as usual, form the quadratic equation, and then press calculator, find out the x value. There are 2 values, one is accepted, another one is ignored. Clear? Then step 4, find the x value, and then step 5, answer the question accordingly. Either ask you to find the pH or the concentration of the H plus, or write down find the Ka or Kb value and so on. You can refer to my video for this part. The third part of pH and pOH calculation is involve buffer solution. If the question given, there are 2 solutions, weak acid and its conjugate base salt, or weak base and its conjugate acid salt. Then you have to apply Henderson-Hasselbalch equation. Okay, so based on this question, very clear a buffer solution is prepared. If the solution didn't mention buffer solution, you have to check, is it acid with its base salt or weak base with its conjugate acid salt? And then there are two equations. Okay, one is the weak acid or weak base dissociate partially. Another one is the salt dissociate completely. Okay, then you write out the Henderson-Hasselbalch equation. pH equal to pKa plus log conjugate base over weak acid. If involved base buffer solution is POH equal to pKb plus log conjugate acid over weak base. Then substitute, must mention what is the concentration of the conjugate base and then what is the concentration of the weak acid. So this one is referred to the conjugate base, NO2 negative. And then this one is the weak acid. And then do is usual. General formula, specific formula. Specific formula means you can substitute the Ka value and then mention what is the conjugate base. The conjugate base is NO2 negative. And then what is the weak acid? HNO2. Okay. Next, still the calculation of pH and POH which related with buffer solution. In this case, when strong acid or strong base is added, what happened to the pH of the buffer solution? Of course, the total volume is changed. The initial mole of the solution have to be calculated. So we need to calculate that the initial mole of the base means the salt, the conjugate base, and the initial mole of the acid. And then this is the number of mole of the acid, strong acid is added. So over here, normally the strong acid or the strong base is added is the limiting reactant. So now we have to calculate the new number of mole, means the final mole of the solution for the conjugate base and the weak acid. Then the total volume of the solution change as well. So we need to recalculate again. Always remember the volume must in liter. So now the new concentration of the final solution, using the new number of mole over the new final volume, you get the new concentration of the conjugate base and the weak acid. Now again, general formula, specific formula, substitute everything. So this is the final pH when the strong acid is added for this reaction. And then we use the original pH of the buffer solution minus the buffer solution after the strong acid is added. So the step involved, again, write down the balance equation, form the ice table. Okay, normally in this part we are deal with the number of mole, and then we calculate the new volume, and then we calculate the new concentration for the acid and conjugate base. Apply the Henderson-Hasselbalch equation to calculate the new pH. Answer the question accordingly, find the difference or the change of the pH. The third focus is about salt. Salt actually is the product of neutralization. It's the reaction between acid and base. It will produce salt and water. So there are three types of salt: neutral salt, acidic salt, and basic salt. Over here, I encourage my student to write down the neutralization equation first in order to help them to identify the reaction whether it's strong acid, strong base, strong acid, weak base, or weak acid, strong base. Because based on the first equation, once you identify the strong acid, strong base, weak acid, or weak base, it can help you to identify what happened to the salt dissociation. Because salt dissociate, and then the third one is salt hydrolysis. Some of you might confuse whether the reaction has the salt hydrolysis equation or not. It depends. If the reaction is come from the weak acid or weak base, yes. Okay, for example, in this case, we know that ammonia is the weak base. So it will form the ammonium chloride. So the weak base will form a strong conjugate acid. Then strong conjugate acid can undergo salt hydrolysis and then produce the H3O+, proven that this is acidic salt, pH less than 7. In this case, strong acid, HCl, and strong base, NaOH. Okay, the conjugate acid or conjugate base is a weak one. So meaning that it won't undergo the salt hydrolysis. Okay. For weak acid, strong base is the same. So this CH3COONA salt, the CH3COONA is from the weak acid. So weak acid, okay, can continue to form the strong conjugate base. So it can continue undergo salt hydrolysis, produce the hydroxide ion, and then the pH of the salt is more than 7. Over here, you must take note. For each of the equation, you must write down the phase. And then Neutralization, one-way arrow, because for forming of the salt and water. Salt dissociation, one-way arrow. And then for the salt hydrolysis is reversible arrow. Please take note. Part 4 is about buffer solution. This part is focused on the explanation of buffer solution. As we know, there are two types of buffer solution. The first one is acidic buffer solution, and the second one is basic buffer solution. Always remember, acidic buffer solution can be prepared from the mixing of a weak acid and its salt, or we call as conjugate base. So we are using the acetic acid or ethanol acid as the example, and its salt or conjugate base is sodium ethanol. Over here, we need to write down three equations. The first one is the buffer solution at equilibrium. This equation is very important when the question asks about the shifting or the equilibrium position of a reaction. Okay, we have to refer. If the concentration of the salt means the sodium ethanol decrease, so the equilibrium shifting will shift to the right. Same for here, when the acid is decreased, and then the equilibrium position will shift to the left. Okay, and then the second part is the reaction that occur in the buffer solution. There are two. The first one is the weak acid partially dissociated, and the second one is the salt completely dissociated. So next, the question will keep on asking, what happened when strong acid is added, and what happened when strong base is added? So this is the action of acidic buffer solution to control pH. So when strong acid is added, okay, and then you must know acid will react with the conjugate base and then form the weak acid. Due to the strong acid totally consumed and then form the weak acid, that's why the concentration H plus remain constant or just slightly change. So we must show the equation as well based on this explanation, and then you must explain, okay, so since this one is react with the acid already, the concentration of the ethanol ion decrease and the concentration of the weak acid increase. Okay, same for here. Okay, this is a reaction when a strong base is added, the base will react with the weak acid, so it will form the conjugate base, sodium ethanol ion, and water. Hence, the hydroxide is consumed, so the pH of the buffer solution just change a bit or slightly change or remain constant. So this is the equation to explain the explanation over here. You must show the equation, one-way arrow. So as a result, what happened? Only a small change in pH, and then the concentration of the acid decrease, and then the concentration of the ethanol ion increase. Okay, the basic buffer solution, the concept still the same. You have to explain is the missing a weak base and its conjugate acid, means the salt. So in this case, we're using the ammonia and the ammonium chloride. Again, this equation is the buffer solution at equilibrium. This is very important. The shifting of the reaction is based on the buffer solution at equilibrium, means based on this equilibrium equation. When ammonia decrease, what happened? The position shift to the left. When ammonium decrease, the position shift to the right. Okay, so these are the two equations occur in the buffer solution: weak base partially dissociated and the salt completely dissociated. Completely one-way arrow, partially reversible. Okay, so this is the explanation of the action of basic buffer solution in the control pH. Concept still the same. Okay. Part 5. Solubility equilibria. Over here, we must know what is the unit for molar solubility, mole per liter. Okay, as we discussed before, right, the unit for solubility is gram per liter. But most of the time, right, during exam, the solubility actually also refer to molar solubility. So please be careful. One tip I can share with you all, if the question asks about the solubility, if the question 1 gram per liter, it will show the unit. If not, right, normally it's in mole per liter. Okay, and then molar solubility mole, and then solubility gram per liter. Okay, next, molar solubility, again, mole solute dissolved in 1 liter saturated solution. Okay. Solubility product is related with the equation. Okay, when an equation is given, you must transform the equation to the KSP, means the solubility product. Okay, always remember, The reactant is in solid, and then the product is in ion. Always remember KSP is product over reactant, but the reactant is solid, so we just ignore. So concentration of calcium 2 plus to the power of 3. And then the concentration of phosphate ion is to the power of 2. Okay. There are two types of calculation involve KSP. The first one is determine KSP from solubility or molar solubility, or determine the solubility or molar solubility from KSP. Ice table is important to help us to solve the problem. For the calculation step, there are involved 5 steps. First, balance equation with phase. Second, ice table. Third, KSP expression. Fourth, answer the question accordingly. And then over here, must write the conclusion after you finish the question. Let's check what is the effect of common ion on solubility. The presence of a common ion will decrease solubility of slightly soluble ionic compound. For example, the addition of sodium chromate soluble salt to a saturated solution of lead chromate. So we can represent the lead chromate with this equation. Dissociate will form the lead ion and chromate ion. And then we have to apply the Le-Chatelier principle. When the sodium chromate ion is added, what happened? The concentration of the chromate ion increased. So the system will shift to the left. Now, this is the KSP. Okay. When the system shifts to the left, it can reduce the concentration of lead ion and chromate ion. Then, effect of the addition of common ion in chromate. So the concentration of this one increase, then some chromate will join or combine with lead to form more solid PD chromate. Okay, lead chromate. Meaning that the solubility for this one decrease. So first, let's X equal to molar solubility of silver bromide in pure water. So first, write out the equation. Okay, always remember it's a reversible equation, and then solid, so silver bromide, partially slightly soluble salt, and then silver plus aqueous plus bromide ion aqueous. So the initial concentration, change of the concentration, and equilibrium concentration. I think you're all quite familiar with this one already. From Kc, Kp, now Ka, Kb, now is Ksp. Okay, 0, 0 at the reactant product side. Okay, so positive X, positive values on the coefficient. So this is the concentration of the species at equilibrium. So KSP is concentration of silver plus times concentration of bromide ion. So X times X equal to X squared equal to this value. And then we set this value and then we get the X equal to 0. The molar solubility is of silver bromide in pure water is 8.8 times 10 to the power of negative 7 molar. Next, less S. Just now using X, now we using S. Is the molar solubility of silver bromide in sodium bromate. So concept still the same, balance equation, I stable. But for this case, the initial concentration of bromide ion is 0.001. Then the change, positive S, so sum up, okay, this is positive S, this is 0.001 plus S. Okay, we assume that S is very small, that's why we ignore the S, so it's meaning that this is equal to 0.001. Okay, so KSP straight away you substitute S times 0.01, then we get 0.001 S. So what is the S value? Okay, just normal calculation divided by 0.001, so we get 7.7 times 10 to the power of negative 10 molar. This is the molar solubility of silver bromide in sodium bromate. Okay, with this this solubility, molar solubility. Okay, if we extend the question, ask you to compare. So what happened? So based on the value here, right, you will notice, okay, the molar solubility of silver bromide in sodium bromate is lower. Why? Because the presence of the common ion Br in sodium bromide solution increase the concentration of the bromide ion, and more bromide ion will react with the sodium. With the silver. Okay, more bromide ion will react with the silver. Thus, the shift of the equilibrium will shift to the left. Hence, increase the formation of silver bromide and decrease or reduce the solubility. Here. So, real question. See you in next video. Good luck for Monday exam and all the best. Thank you for watching. Don't forget to subscribe, like, and share this video. Bye.